Yeah, thanks for the introduction, and thanks a lot for the invitation to give a talk here. I'm sorry I couldn't come in person. We also have a conference in Zurich this week, so yeah, unfortunately I couldn't really join for much, and now need to give the talk online. But I hope, yeah, you already had a good workshop also over the last weeks and this week as well. I'll now try to share my screen, and yeah, as I tried it before, I just assumed that it still works and you can see what exactly you can see what I'm writing here. Yeah, as you said, my talk is about high-dimensional rational cohomology of SLNZ and SP2NZ. And basically, most of what I will talk about, basically everything, is joint work with Jeremy Miller, Peter Pabst, Robin Skolka, and Jenny Wilson. And most of my talk will actually be about high-dimensional rational cohomology of SLNZ. And so the object I want to talk about is h to the k of SLNZ with coefficients in Q. And the story I'll tell about this is very similar actually to what those of you that were already in the last 2 weeks there saw in the mini courses on the mini course of Jenny and Peter. So I won't assume that that everyone knows what happened in these courses. So for everyone who already saw something in the courses, I will do basically a quick repetition in the first part of my talk of what exactly the strategy is that they explained. And then we'll say something about our contributions, something new in the second half of the talk. And for those who weren't there, I think it should be sufficient what I explained here. Actually, I can't see anyone in the audience, but is it somehow possible to get feedback on how many of you there were at these mini courses of Jenny and Peter? I mean, usually I would ask people to raise their hands, but I see only the board somehow.
Yeah, it's like almost all the people were there.
Sorry, I couldn't hear you.
All the people were already there.
All the people were there. Okay, perfect. Yeah, then it's basically a summary. But I think it's still good to put together what exactly happened there. So as I said, I'll speak about hk of SLNZ with coefficients of Q. And I will be interested in this for the highest possibly interesting k. Yeah, so what do I mean with highest interesting? Well, the virtual cohomological dimension of this group is equal to n choose 2. And I'll just call this D from now on. So this in particular implies that for all k greater than this, hk with coefficients in Q is 0. Yeah, so this is definitely not the highest interesting one. It becomes interesting starting from the VCD. Now, what happens just below the VCD? This is and also something you already saw in Jenny's talk, I think. So right at the VCD, HD of SLNZ is trivial. And this is true for all n greater than or equal to 2, which is that's a result of Lee-Schaber, this from 76. But you actually then also saw a proof of this in Jenny's course last week, where she used the result of Ash and Rudolph to show this result. Okay, so that's maybe also not the most interesting one, the cohomology in the VCD. If we go one below, so HD minus 1 of this group, it's still maybe not the most interesting one because it's also trivial. And this is now true whenever n is at least 3. And this is a result by Church and Putnam from 2017. This is what you saw, what Peter talked about in his course in the last week. And okay, now the cohomology is trivial in the VCD if n is at least 2. It's trivial 1 below. So codimension 1 is trivial if the n is at least 3. it's maybe not too, I don't know, adventurous to guess that this might be a more general pattern. And in fact, there is a conjecture by Church, Farb, and Putman that says that maybe this is a bigger pattern. Namely, they conjecture that the co-dimension I cohomology of SL and Z with coefficients in Q is trivial whenever n is sufficiently large, and sufficiently large here means n is at least I plus 2. Okay, and okay, these two results that I wrote down here say that the conjecture is true for I equal to 1 and I equal to 0. Yeah, this is I equal 0, this is I equal 1. And the result that I want to talk about in my talk is that it's also true for I equal to 2. And that is a joint result of Jeremy Miller, Peter Putzt, Robin Sruka, and Jenny Wilson and myself from this year. So, okay, it's true that the conjecture is true for I equal to 2. That is H d minus 2 of SL and Z with coefficients in Q is trivial whenever n is at least, well, 4 would be the conjecture. We actually show it for n equal to 3. Yeah, but in particular, it's also trivial for n at least 4. Okay, so this is the result that I would like to talk about. And my talk maybe roughly has 3 parts. Beginning, I will outline again the strategy of this proof of Church and Putman, which should for many of you be familiar because of the talks of Peter and Jenny. Then I will talk about our contributions for this theorem. And there I'll mainly focus on one thing, because what we do, the general approach that we use to show our result here is quite similar to the one of Church and Putman. But at some points, the combinatorics for this codimension 2 setting gets significantly more involved than for the codimension 1 statement. And we use computers to help us to, I don't know, cope with this combinatorics. And I thought it would fit in well with the scheme or the theme here of this conference in general, to give you a bit of an idea of how we use computers to do that. Yeah, I won't be able to go in all details, but I try to give you an idea how we use computers in our argument. So that's the second thing. And then, okay, at the very end, I'll say some words about the setting of SP2NZ. Okay, but I'll start with the outline of the strategy by Church and Putman. So the first main ingredient that we need for this is Borel-Serre quantification, which gives us a duality. So it follows from a result by Borel and Serre that there is the following duality for the cohomology and homology of SL and Z. Namely, it is true that h to the d minus I of SL and Z with coefficients in Q is isomorphic to hi of SL and Z, but now with coefficients in Steinberg module tensor Q. And so slightly twisted coefficients. And this STN is what's called the Steinberg module for SL and Q. And this is the same as the n minus second homology of a simplicial complex, namely of the Tietz building associated to SL and Q. Okay, so this is something, this duality result here is something that Peter talked about in his first lecture also. But even without taking into account what that is, yeah, you can just accept this isomorphism between the two things. So basically it tells us that to compute the high dimensional cohomology of SL and Z, the object on the left-hand side that I will be interested in for this talk, You can instead also compute the low-dimensional cohomology of the group, but the trade-off is that you get more complicated coefficient, namely this Steinberg N tensor Q. And let me remind you what this is. So the Steinberg module, as I said, here is the homology of a certain simplicially complex, namely the building associated to SL and Q. And this is the following simplicially complex. So it's a simplicially complex. The vertices of this complex are proper subspaces of Q to the N. Yeah, with proper I mean non-zero and not equal to all of Q to the N. This is an N. And the K simplices in this complex are given by chains of such subspaces. Yeah, so there's a K simplex whenever the corresponding vertices form such an ascending chain V0 until Vk. That is a simplicity complex, and I mean, this is an object that is studied very much in much more general settings, which was introduced by Jacques Dietz originally. But for the purposes here, it's sufficient to know that it's a highly symmetric simplicity complex, that SL and Z acts on this complex, namely just because if you apply an element of SL and Z to subspace of Q to the N, you get again subspace of Q to the N. And the topology of this complex is very simple, namely it's homotopy equivalent to a wedge of spheres of dimension n-2. So in particular, it has only one non-trivial homology group, and that is its n-2nd homology group, which is exactly the Steinberg module that showed up in the coefficients on the right-hand side above. Okay, so what does this duality tell us? It tells us that if we want to understand the left-hand side of this equation here, what we need to do is to understand this module, Steinberg module on the right-hand side, we need to understand this thing very well as an SLN-Z module. And a bit more precisely, what do I mean with understand it well as an SLN-Z module? The following is true. Well, I mean, this lemma, okay, in this form it's stated in the article I mentioned above, Church and Putman, but it's really just general homological algebra. And Jenny also mentioned it in her talk. The following is true. Let's assume we have a resolution like this of Steinberg N tensor Q. So this is a resolution by flat SLN Z modules, CI. Then if we can show that the co-invariance of CI is trivial, so if for some I these co-invariants are trivial, then we get that also the homology of SL and Z in these coefficients is trivial. Yeah, this is really just a general argument. But by Borel-Serre duality above, this is isomorphic to HD minus I of SL and Z, now with the coefficients we're really interested in, namely rational coefficients. Okay, so in order to show these vanishing results for the homology, the strategy is basically to get partial resolutions of this module by SL and Z modules. And these partial resolutions need to be explicit or nice enough for us to be able to compute the co-invariance of SL and Z of this module, to be able to show that it's trivial. And this is what Church and Putman do in their work, namely they find partial resolution of length, maybe you would call it length 1 or length 2. Well, it starts at C1, then there's C0, and then it goes to the Steinberg module. So they get an explicit resolution or partial resolution of the module like this. And by the way, what Jenny mentioned in her, and they use this to show that the codimension 1 cohomology of the group is vanishing. By the way, what Jenny did in her talk was to explain that this part here, from C0 to Steinberg of n, okay, maybe what does it mean to have a partial resolution only of length 0? So this is just a surjective map from this C0 to Steinberg of n, tensor Q. This means this gives exactly a generating set for the module. This is the same as a resolution of length 0, partial resolution. And this was what in Jenny's talk was the result of Esch and Rudolph that give a generating set for this module. Yeah, but more generally, one can state it in terms of such a partial resolution. And okay, then now the key step that Church and Putman use in order to obtain such a resolution getting the resolution is to show that a certain simplicity complex which they call BAN is n-1 connected. Yeah, so it's homology groups when it's higher homotopy groups vanish up to n-1, or in other words, whenever you have sphere of dimension at most n-1 that maps into the space, then you can extend it over a ball whose boundary is that sphere. Yeah, and then I won't go too much into detail, but then roughly speaking, if these complexes are highly connected enough, then one gets a resolution in terms of relative homology groups of these complexes. Now, what do these complexes look like? Maybe to give you an idea, what this complex BA looks like is you do the following. You start by defining a complex BN without an A. And BN is a simplicity complex whose vertices are exactly the lines in Z to the N. So the one-dimensional summons in Z to the N. Yeah, this is not exactly the complex that Jenny had in her course, where it was about this PBN partial basis, but it's a very related one, very closely related one. So the vertices are one-dimensional lines, and the K-simplices in this simplicity complex are collections of such lines that together form a partial basis in Z to the N. Yes, and such that you can extend all the set V0 until Vk to a basis of Z to the N. Okay, that's the complex Bn. And what is true, this is shown in an article by Church, Farb, and Putman in a more general setting, is that this complex is n-2 connected. And maybe I think here it would be good. You probably already saw such a picture in Peter's talk, but I think it would be good to give you an idea of why this might be a reasonable thing to believe, that this thing is n-2 connected. And for this, I'll draw the situation if n is equal to 2. So if n is equal to 2, then well, let's write Z squared as the group generated by E1 and E2. Okay, now what are the vertices of the complex B2? These are the one-dimensional lines in, well, in Z squared. So for example, there is the span of E1. And there is also the span of E2. And these two together form a basis of Z squared. So they're connected by an edge. Then there is also the line spanned by E1 plus E2. And this is also E1 plus E2 together with E1 forms the basis of Z squared, and also together with E2 it forms a basis. And then there's also, for example, the line spanned by 2 times E1 plus E2. This forms, again, a basis together with E1. It also forms a basis together with E1 plus E2, but it does not form a basis together with E2. Yeah, because if you take E2 And this thing then, well, formally there is some determinant that is not invertible, or I mean, you just sum them up. No matter how often you sum them up, you will always get an even multiple of the E1 coordinate. So in particular, there's no edge between these two vertices. Well, and then you can go on and draw all the other vertices. E1 minus E2, for example, is such a line that is connected to these. And well, you can go on like this, and when you complete the picture, it turns out that the object you get is actually the fairy graph. So it's a graph that is in particular connected, well, but has non-trivial first homology. So in particular, this thing is zero connected, which is good because that's n minus 2, and that's what I claimed. It's 2 minus 2, so 0 connected, but it's not 1 connected. Okay, so much for the example. Then, but now I said that Church and Putnam use another complex that is called BAN. And BAN can be constructed starting from BN, namely the vertices of BAN are just exactly the same as the vertices of BN. Yeah, again, lines in Z to the n. The higher dimensional simplices are, well, first you take all simplices you have in BN, so these collections of partial bases, and then you add new simplices that are of the following form. They are collections that have a partial basis here, but then they also have one vertex which is allowed to be the sum of two of the others. Yeah, so this is one new type of simplex basically you get in this complex. And then what Church and Putnam show is that this complex now is n minus 1 connected. So 1 higher connected than Bn. And again, let me look at the picture above to show you that this is a reasonable thing to believe. So what do we glue in here? What is the new type of simplex? Maybe I'll do it in light blue. This new type of simplex here has, well, first a partial basis and then a third thing that is the sum of two of them. So for example, this triangle here. Or this triangle here. Yeah, you have E1, you have E1 plus E2, and their sum, which is 2E1 plus E2. And then you also get, well, all the other triangles in this picture. So in the end, actually, in this case, for n equal to 2, you get even a contractible complex. You glue in basically all holes that show up in this graph are glued in, which means that it's now not only connected, but it's also simply connected. So it has trivial fundamental group. Okay, and for higher n, it's harder to show, but it's also true. Now, what do we do in our article? So this is now what Church and Putnam did up to here. What we do to get a resolution of length 2 is the following. We define another complex, which we call BAAN. And this complex has all simplices that BAN has, plus some new types. And to save myself some time, I won't write down the new types here, but it's also you allow certain other constellations of lines in Z to the n. And what we show is that this complex that we obtain is now even one higher connected, it's n connected. And from this we get as a corollary, that this is HD minus 2, the VCD of SL and Z with coefficients in Q is equal to 0. And the proof of this corollary is very similar to the strategy I outlined for Church and Putnam, or that you also saw in Peter's and Jenny's talks for the codimension 0 and codimension 1 cohomology. you need to think a bit about how you get from such a highly connected complex a partial resolution, but you can do it. And this is more a general homological algebra argument. Then you get this explicit partial resolution that is somehow explicit in the sense that the generators of each of the chain modules Ci is somehow generated by certain types of simplices in this complex BAN. Okay, but that's more of kind of a detail. The important thing, it's explicit, and you can very well describe the action of SL and Z on these Ci. And then you use the result I wrote up here to show that the co-invariants C2 of this thing vanish, to show that the cohomology is also trivial in codimension 2.
Could I ask a question?
Yes, sure.
I know you don't want to say what they are, but can you say how many they are? Like how many different new types you had to add?
Yes, 3 new types.
Okay.
Three new types. I mean, I can also write down one at the end if you want, but it's 3 new types. Yes. Okay. So, as I said, once one has the connectivity of this complex, one needs to think a little bit about it and compute actually the co-invariants. But that is quite similar to what Church and Putnam do. And it's more of a general homological algebra argument. Really, the main work that we need to do, and that's almost all of our article, is to show that this complex is n-connected. This is really the thing where where the work and explicit combinatorics goes in for us. And for this, to show that this is highly connected, this is where we also use computers to help us with some things. And the main reason that we need to use these computers are exactly the number of types of simplices that we get. So in this complex BAN of Church and Putnam, there were 2 types, right? The partial bases. This is one type. Oh, sorry, this is one type. And then there's a second type that were these 2 additive, we call them simplices, yeah, because 2 things add together to a third thing. But now we get 3 more types, and you have to somehow work in these complex with many types of simplices, and the combinatorics gets hard, and this is where we use a computer to help us. Now, of course, these complexes are infinite, so one can't just a priori compute their homology with a computer and use that to get helpful results. But I would like to at least give you, as I said, I think in the setting here for the workshop, it might be good to give at least a small idea of how we reduce this infinite problem, basically of computing the homology, the homological groups of an infinite complex to a finite problem that we can insert in a computer. And this is what I would like to give you a rough idea of now. Yeah. So I would like to give you a very rough outline of the proof of this theorem. And it's quite a long proof, so I will skip many steps, but I'll just try to give you an idea of where computers come into play for us. So proof idea of the theorem above. What do we need to show? Well, we need to assume that we have the map from a K-sphere, SK, into our complex BAAN, and that K is at most n. And our aim is to show that this map from a K-sphere extends over a K+1 ball. Then we're done. This exactly means that the complex is n-connected. And now we do this by homotoping step by step this map phi to another simpler map, And in order to keep track of the complexity of the map that we want to reduce in these steps, we define the following rank. And this is something you also probably saw in Jenny's talk. Our measure of complexity is that the rank of a vertex is just the absolute value of its last entry, or of its en coordinate, if you want, if it's generated, if z to the n is, every vertex of BAN is a line in z to the n. In particular, the absolute value of its last entry, of its en coordinate, is well defined. And this is the complexity measure we take for a vertex. And now our aim is to reduce the so there are several vertices in the image of phi, and our aim is to reduce the rank of these vertices such that in the end, all vertices in the image of phi have last entry equal to 0. So aim is reduce image of phi to rank 0. Yeah, this is a bit informal. Yeah, what I mean is, yeah, what I said, every vertex has last coordinate 0. And if this is the case, one needs to think a bit about this. But if we get such a map where everything is last entry is equal to 0, then it's actually true that we have a sphere, I don't know, a sphere like this. This is our SK in BAAN. And then it's actually true that a single vertex spanned by EN forms a cone point to this sphere. So there is a ball that has at its center EN, and everything else is connected to it. Yeah, well, this is not so clear definitely not clear because I didn't give you the entire definition of the complex, but this is the aim. Reduce the last entry of every vertex in the image to 0. Now this is done inductively. So if we map the sphere into the complex, well, the sphere is compact, so it hits only finitely many vertices. That means there is a maximal last entry that we get somewhere at some step. Let's say that this maximal last entry, so inductively, maximal entry is R. Maximal rank in image of phi is, let's say, some R that is now greater than 0. Then the picture looks roughly like this. So here we get a sphere SK, and it somehow maps into the complex BAAN. So maybe our sphere looks like this is a part of the sphere. So here K would be equal to 1. Let's say this is the vertex X, and X is maximally bad in the sense that it maps to a vertex phi of X that has rank R. Yeah, so this is one of the worst vertices we can get in the image. Now our aim is to avoid having this vertex in the image. And if we do this for all without introducing something new, really bad, then the rank goes down slowly, step by step. What we do for this is, well, okay, let's say, so this phi of X, then somehow it goes on like this. So what we do is on the left-hand side, we have, in this case, 2 points here, which are the link of X. Yeah, so the link of X are just all simplices in the sphere that form together with the point X another simplex. In this case, the 2 endpoints of the other edges, of the 2 edges adjacent to X. And this maps somewhere here to the right. So this is phi of the link of X. Now, where does this map to? Well, it actually maps to a certain subcomplex here on the right-hand side. Maybe I'll draw it in green. And this subcomplex is, so this is contained in the subcomplex link of phi of X. So this is clear because the link of phi of X are just all simplices, all simplices that form a simplex together with phi of X. And as the map is simplicial, if they form such a simplex on the left-hand side, they also form a simplex on the right-hand side. And now let's assume that we already have isolated somehow our problematic vertex phi, and let's assume that if X is sent to something of rank R, then at least the things right next to it are not also sent to something of rank R. So I write a smaller R to say that this is an area where everything has rank at most R. Now, let's assume that we knew that this thing here was highly connected. If it was highly connected, so for example, like the green thing I drew above, if it is connected, then what we can do is we can, in this complex, connect the endpoints, I mean the link, fill in the link of X. Link of X will actually always be a sphere, and it maps to a sphere in here. Then we can fill it in this lower complex, and then what we can do is everything here forms a simplex with phi of X. So that means that all of these are simplices, and we can homotope our map by pushing down this phi of X at the top to this filling that we have at the bottom. Yeah, so we push down phi of x to something that is an area where everything has rank at most r. And this we can do if we know that this is highly connected. It needs to be highly connected. Okay. And what is actually not too hard to show by induction is that the link of phi of x is highly connected. Yeah, I won't go into this now, but this is somehow an inductive procedure. The problem is we also want to know that the part of the link that only contains the vertices of rank at most r is also highly connected. And this is what makes it difficult. And in order to get this, what we do is we construct a retraction from the link of phi of x to this link smaller r of phi of x. And if we have such a retraction and this thing is highly connected, then it also follows that this thing is highly connected, which is what we want. So that reduced the entire problem basically to a local picture of, well, it's not so much of a, well, it's a local picture around every vertex phi of x. We need to be able to push our, to retract our link to this area of the link where every vertex has rank at most r. And the definition of this map now is done by looking at the different types of simplices and defining the retraction for all the types one after the other. And this is exactly where we use a computer to handle the different types that we get. Yeah, and the problem that we, so I still have like around 10 minutes, right?
That's right.
Okay, then okay, let me just, so roughly the outline. So now we are up to, so what we achieved now is we need to define such a map from here to here. And it just needs to be, well, a simplicial map. Surjective, okay, but surjective will be easy. Yeah, we just need to have a simplicial map from this link to the other thing on the right-hand side. And now in the link, there are different types of simplices. And for every such type, we want to define the map. And how a computer will help us is it will compute certain finite the homology of certain finite subcomplexes of this or of this thing on the right hand side. And I'll show you now how, or give you an idea of how. So what is the idea? As I said, we define it define R one type after the other, one type of simplex after the other. Okay, I'll start with the vertices. Or let's say I'll do the partial bases. So the first type, remember in BA there were two types, namely these partial bases and these additive things. So I'll start with the partial bases like this. Now I have such a vertex, let's say a vertex, just a single primitive vector. This is some vector in the link of phi of x, so it forms a basis or partial base with phi of x. And we need to send it to something in the link smaller, so to something that has last entry at most r, or absolute value at most r, and still forms a partial basis with phi of x. Now, by assumption, phi of x is something that has last entry equal to r. But that means that by the Euclidean algorithm, we actually find an element q in Z such that vi, the vertex we start with, minus q times phi of x has last entry at most r. Yeah, this has at most r, this has something large as last entries. We can just, we can just subtract phi of x until we reach the area between minus r and r. And this is certainly something that lies in here. Okay, I think Jenny actually also defined it already like this in her talk. Okay, and this defines it for vertices here. And now I just claim that for simplices, you define this map vertex-wise, and it induces a map on the simplices. Okay, so good, so far so good. But now we come to the next type. There was one more type in EA, and these were simplices like this. Now, again, we want to define a retraction on these simplices. Okay, maybe let's write this again. We have link of phi of x, and we want to map it into link smaller of phi of x. And now we have a triangle on the left-hand side that looks like this. E0. I'll not write span, yeah? I mean, it always means span, but I won't write it just to save some time. It looks like this. Okay, but now we already defined the map on partial basis. And this is a partial basis of z to the n. And if this is a partial basis, then these two together also form a partial basis. And these two together also form a partial basis. And for the partial basis, we already find our map. So we already know that the image of the surrounding triangle is some kind of triangle here on the right-hand side. And our aim is to extend this map on the triangle to a map on in the interior. This is exactly what we need to do to extend it over this type of simplex. Okay, but what does that mean? Well, what's the boundary of this triangle? The boundary of this triangle is, well, in this case, it's isomorphic to a one sphere. And we already defined this map from the one sphere into the complex on the right-hand side. Now, if we could show that the image of this triangle lies in a subcomplex on the right-hand side that is simply connected, that is one connected, then we know that we can definitely find a way of extending it over the ball, namely this triangle, whose boundary the sphere is. So what we need in order to define this is we need to find a one connected subcomplex say x of delta of this triangle that contains our triangle on the right-hand side. And now this is what we use a computer for. Basically what we do is, given such vertices as the input on the left-hand side, v0, v1, and the sum of them, we, I'll say we guess vertices of the complex x of delta. And then what the computer does is, so we make sure that all our guesses only have finitely many vertices. And then what the computer does is it shows that the complex is actually one connected. And well, okay, actually it also lists all cases that can occur. Yeah, one needs to make sure that there are only finitely many cases that can occur. This is not so clear, but in the end, that's what we're doing. Now, yeah, I lied to you a little bit. Yeah, these type of simplices actually are not so hard to handle. They are already in the work of Church and Putman, and there they don't use computers to do this. They do it by hand to find this complex and show that they're one connected. But as I said, in our complex later on, we get more types of simplices. But the principle will always be the same. For every such new type of simplices, we know where the boundary of the simplex, which is a sphere of certain dimension, we know where it gets mapped. And then we need to find a subcomplex, a finite, well, we could also find infinite, but we can find a finite subcomplex of the image that is sufficiently high connected. And this implies that our map extends over simplices of this type. And then the computer needs to show that these finite subcomplexes are actually highly connected. And okay, highly connected in this case means it suffices to show that their homology groups vanish and the fundamental group vanish. But the fundamental group vanishing is very simple. And the rest is where we actually need the computer to do the work for us. Yeah, I guess my time is almost over. I think instead of saying more about the SP2 and Z case, maybe I'll sum a bit up what I did here. I think that's maybe more reasonable now. So what is our aim? Our aim is when we need to show that a certain complex BAA is highly connected. If we get this, then the procedure of Church and Putman that also Peter and Jenny explained last week actually allows us to show that the codimension 2 cohomology of SL and Z vanishes with rational coefficients. And in order to show that this infinite complex is highly connected, what we do is we inductively try to reduce the complexity of spheres that map into our complex. And that makes this global argument of having the complex to be highly connected to become much more local, in the sense that we need to define certain maps over finitely many types of simplices, and we always need to show that these simplices map into subcomplexes that are highly connected. And as these subcomplexes are finite, we can use a computer to compute their homology and to tell us that they are highly connected. Yeah, right. So in the end, I mean, in principle, of course, one could also do it by hand, but yeah, there are just many cases, and already like that, we have a lot of case distinctions in the paper, basically everywhere where we don't use a computer. So we were quite happy that at least part of it could be covered by the computer argument. And then maybe just to finish, really just in words, I'll say that I'm currently also working with Robin Sroka and Peter Patzt on an analogous result for the symplectic group SP2 and Z. There it is known that the cohomology vanishes in codimension 0. This can be deduced from a result of Paul Gunnels. And we are working on the codimension 1 case. So we are currently trying to find out whether it also vanishes in codimension 1. The things in principle can be done rather similarly. Again, one needs to define a certain complex and show that it's highly connected in order to get a resolution. And we think that we now have the proof, and we are currently writing things up. What we have not done yet is to use this to actually compute the resolution and check whether the cohomology vanishes. But I don't know, we are mildly optimistic that we'll get it done, say, until autumn, somewhere in this summer, hopefully. Yeah, that's all. Thanks for your attention.
Okay, let's thank the speaker. Can't tell. I don't hear anything, but I assume there's enthusiastic applause.
Yes. Oh, you didn't hear?
I didn't hear anything. I don't know if the speaker heard anything.
No, I also didn't hear anything. Yeah.
Okay, that's
Probably
that's
good noise cancelling. Yeah.
Are there any
Sorry.
questions?
Well, I will. Okay, I will just the comments for Benjamin. So you didn't say about the noon results, and I just wanted to comment on the fact that it was noon up to n equals 11.
Oh, sorry. That the vanishing is actually true.
Yes.
Yes. Oh, yeah. Yeah. I'm sorry. Yeah. That is true. I did not talk at all about. That is true. Yeah. I'm sorry. I did not talk at all. You're right in the beginning about say low-dimensional cases that are known, where there is much more known than. I mean, if you want, what we know is really only it's an infinite but very tiny strip. Whereas this was definitely already, whereas this was already known for low dimensions in more cases than what we can show. Yeah.
So there were a question in the chat. It's why.
No, that's sorry. Well, actually can't see the chat, I think, but
no, maybe not. No, but it.
But no, sorry, you're right. Yeah, I didn't cover at all. That is true. It's not like I focused a bit to the very yeah, you're right. Sorry.
I also wanted to ask if it's possible to turn these results into formulas for like principal congruent subgroup. like was done in the top dimension, top degree?
I mean, we have some, we actually have some non-vanishing results for the homology of congruent subgroups but that is in co-dimension 1. We also get that, though I should say one doesn't really get it from the exact resolution that we have. Instead, one rather gets it from very similar techniques somehow, but one needs ingredients about other complexes associated to these congruent subgroups or to finite reversions of it. So yeah, that's possible, but we needed to also use results of what is it, Miller, Nagpal, for that. So we also get results in that direction, but it's not immediate from exactly this resolution.
I see.
And we get in co-dimension 1.
Okay. Philippe, did you have another question?
Yeah, well, you should. Well, I think it was already discussed by Peter, but I think that you should be able to do Gaussian integers and Eisenstein integers. It's just the last computation will be a little bit more difficult, but still doable, I think. Do you share this?
This would also be my impression. Yes, right. For the co-dimension 1 case, there. Right, this is done. So I also think we could probably also do it for that, but we haven't. Yeah, we haven't looked into this, but I would also be optimistic.
Any questions or comments on our side? No, Paul. So no more questions.
Okay. All right. Well, let's thank the speaker again for this excellent talk.
Thanks.